Dr. Hendley is a first-year physics resident in our department, and today he's going to talk about his PhD work conducted at University of Chicago using ultrasound, which is usually not an therapeutic agent. We usually use ionization radiation for therapeutic purposes. So let's hear about this innovative research.
Yeah, thank you very much for that introduction. So as Dan said, this is a non-ionizing form of treatment. So I know this is kind of the black sheep right now, but I think this would be a very kind of interesting up and coming therapy that will be good to know about. So specifically, my work centered around using this sort of techniques for deep vein thrombosis. So as you can see from my title, I'm going to be talking about using ultrasound as an adjuvant therapy for deep vein thrombosis. So I know I'm speaking to kind of a wide audience here today, so I'm going to start by talking with the broad clinical scope, and then I'm going to talk about the physics and then how those two combine together. So first off, for some motivation, why do we care about deep vein thrombosis in the first place? Well, for some statistics, DVT affects about 5% of the United States population. It accrues approximately $10 billion in healthcare costs per year. And what's interesting too is that more than 80% of pulmonary emboli are caused by DVT, usually in the iliofemoral vasculature. Additionally, when there are critical obstructions, those require critical intervention too. So a lot of times you can't just leave the thrombus there, you have to intervene. Now, what's kind of interesting is that not all thrombi are homogeneous in structure. So pictured at the right here is a histological cross-section of a venous thrombus stained with Masson's trichrome. So the magenta portions indicate more so fibrin components that one might generally see in an acute thrombus. So we can think about the acute thrombus as generally a mass of red blood cells held together by a mesh made of fibrin. We can use drugs called thrombolytics to chemically lyse and break down the thrombus. In the US, the thrombolytic that we use the most for this is TPA, and this drug is actually specific to fibrin. That means it's going to preferentially target fibrin and try and break down that mesh. And what's great is that this treatment actually works very well for acute thrombi. However, this technique doesn't really work so great for chronic thrombi. While the numbers vary, a significant proportion of DVT cases involve chronic components. So like the acute thrombi, they contain a fibrin mesh structure, but unlike the acute thrombi, the chronic thrombus also contains a secondary network made of collagen, and it's less susceptible to thrombolytic therapy. So in the same histological image, you can see the collagen matrix around here, highlighted dark blue. So in these sorts of cases, TPA may not be the best course of action, as these clots are more resistant to TPA, and long exposures to TPA are associated with bleeding complications. And I really want to touch on that last point because I feel like that's kind of the crux of these studies. So thrombolytics are typically infused over the course of about 12 to 24 hours usually, and the administrative and financial costs really do add up for these long treatments. Additionally, there's a risk using thrombolytics as undue bleeding and hemorrhage becomes more likely as lytic dose increases. So if we know that thrombolytic therapy alone isn't effective for all cases, then we need some kind of a way to increase its efficacy. And this is where histotripsy comes in. So histotripsy comes from the Greek histo meaning tissue, and then tripsy meaning to break apart. That's literally what we're trying to do here is break apart tissue. So histotripsy is a mechanical form of therapeutic ultrasound that uses the mechanical action of bubbles for two main effects. So first is mechanical destruction. So when the peak negative pressure of a waveform, so seen here is the waveform, so when that peak negative pressure dips below the nucleation threshold, that's part of the medium, then a nanoscale nucleus seen here will rapidly expand all the way up to hundreds of microns in diameter, and this happens very quickly. And this sort of action imparts lethal strain on the surrounding medium and actually destroys tissue. Now, what's kind of great is that these nuclei themselves are intrinsic to water and soft tissue, so we actually don't have to add any nuclei to make this occur. And for those visual learners out here, I think this is a great example of histotripsy in action. So this is just captured with a normal camera, so you can see the bubble cloud itself expanding and collapsing in real time. So on the left-hand side is our transducer. So this generates the ultrasound waves, which are very tightly focused into this zone seen here. And for scale, our focus that we use for our experiments are generally the size of about a grain of rice. So it's a very small focal volume. So in addition to this sort of damage that we see, There's also the idea of improved drug delivery. So the oscillations of these bubbles can also induce fluid mixing and even permeabilize the tissue. That makes it a lot more easy for us to get the drugs to where they need to go, especially when you have stiff kinds of tissues. It makes it a lot easier. So these two bioeffects, mechanical damage on one hand and enhanced drug delivery on the other, can combine synergistically to eradicate thrombi. So that's the general scope of what I'll be talking about today. So this brings me to my main hypothesis, which is that combining histotripsy with lytic therapy will help disintegrate clot tissue. So this was examined in two ways. So in the first study that I'll talk about today, the lytic dose is held constant as the insonation conditions are modified. And in the second study, the lytic dose is changed while the insonation conditions are constant. So I touched earlier on the sort of mechanisms in general of how it works, but I want to hone in now and talk about how those mechanisms would affect clot tissue itself. So like before, right, I hypothesized that histotripsy helps break down clots by these two main mechanisms. So first is a sort of mechanical damage. In this case, it takes the form of hemolysis, and this is where the red blood cells themselves are ripped apart by that intense tensile pressure made by the bubble cloud. And what's good is that this hemolysis itself is a very good indicator of general mechanical ablation, right? If you see more hemoglobin, then you're assuming that there's more mechanical damage that's occurring. And second is fibrinolysis. So when the thrombolytic drugs like TPA act on a clot, it lyses the clot's fibrin network and produces detectable amounts of what are called fibrin degradation products, such as D-dimer seen here. So here's our fibrin mesh, and it's being cleaved to form this small product D-dimer. So histotripsy might, as I said before, might help enhance fibrinolysis by improving drug penetration, and mechanical hemolysis itself liberates hemoglobin. So we can kind of use those two ideas. So D-dimer can help us measure fibrinolysis and the sort of fluid mixing. And we can use hemoglobin to help measure the sort of more mechanical side of what's happening. Overall, these two mechanisms contribute to treatment efficacy as measured by mass loss. So the studies that I've been looking at are all in vitro studies. So the kind of the best model we have right now for efficacy is mass loss. So you just measure the mass of the clot before and after and compare what happens. So this brings me to my primary question for this study, which is how do these mechanisms actually relate to treatment efficacy, right? There's the idea that is it possible that the mechanical hemolysis matters more, or does chemical fibrinolysis matter more? So to study this, I use the following methods. So this is an IRB approved protocol. So we draw 2 milliliter aliquots of blood, transfer them into glass Pasteur pipettes. We incubate the blood at physiologic temperatures for about 3 hours, and then we store them at 4 degrees Celsius for 3 days to allow for full retraction. And you can see the clots here. So afterwards, we place our clot into our flow channel system. So here's our clot inside our flow channel system. And then plasma with or without thrombolytic is added at flow rates representative of slow ileofemoral flow. And you see our histotripsy transducer here. Here's a little inset over here of our transducer. So this transducer will scan and treat along the length of the 1 centimeter long clot with treatment points spaced about 0.5 millimeter apart. If you're interested in the physics here, I listed my parameters that I used. If you're not a physicist, let me just tell you right now that 35 megapascal peak negative pressure is huge. That is a gigantic pressure that we're working with. So we're spanning a very large range here. And I also want to talk about how we actually measure our D-dimer and hemoglobin. So after each treatment, the perfusate is collected, which consists of plasma and any sort of clot debris. So I want to call your attention to this image down here of these two beakers. So this image actually shows the difference in perfusate for clots exposed to either plasma alone, as seen on the left, or clots exposed to histotripsy and lytic on the right. So just as you can tell that there's a difference in color, that means that there's probably a difference in perfusate and debris content in there. So what we can do is we can use an absorbance assay to actually calculate the concentration of hemoglobin. Likewise, we can actually just use a very common clinical D-dimer latex turbidity assay for measuring D-dimer. And again, just to remind you, our overall treatment efficacy that we're looking at is mass loss, looking at the mass of the clot before and after treatment. So without further ado, I want to jump into kind of our exciting results here. So here we're comparing the effect of fibrinolysis, so on the right-hand side, D-dimer versus mass loss, And on the left-hand side, we're looking at hemolysis versus mass loss. So these are all for clots that are exposed to a single amount of lytic, so 2.68 micrograms per milliliter of TPA. And each point on these scatter plots corresponds to exactly one clot. So what's kind of cool is that we see that for clots exposed to lytic, fibrinolysis and hemolysis both tend to increase with mass loss. And what's actually very interesting too is that the slopes of these two plots are not significantly different, suggesting that both hemolysis and fibrinolysis contribute roughly equally to treatment efficacy. Now, there's a different story if we don't apply any lytic at all, right? So just like before, we do see a link between hemolysis and mass loss, even without any TPA. So there's still that sort of mechanical action that's occurring. However, if we look at D-dimer, we see no such trend, right? And that may surprise you at first, but this actually makes perfect sense because the action of TPA is necessary to form and to cleave those D-dimer products in the first place. So it makes sense that we're not really seeing a connection between D-dimer and mass loss. So to wrap up this first study, I want to drive home two main points. First is that we know that histotripsy is an effective adjuvant therapy for thrombolysis, so we know it works. Secondly, I think what's very interesting about this sort of study is that we've shown that hemolysis and fibrinolysis contribute roughly equally to overall treatment efficacy. So it's important for us when we're designing treatments in the future to harness both of those mechanisms and not just one of them. So for the second half of these studies, I looked at what happens when the lytic dose varies. So I'm sure all of you know that lytic can be administered in two kinds of ways, systemically, or can be delivered, in this case, through a catheter. So in the systemic approach, right, lytic is given through an IV. It circulates within the bloodstream until it reaches the clot. Now, for historical reasons, my previous lab only used the systemic thrombolysis in the previous studies. However, we know that this is less common clinically in comparison to using catheter-directed thrombolysis, or CDT, where we use a catheter to deliver TPA in close proximity to the target or clot. With this in mind, I want to discuss some more of my experimental methods in more detail. This plot should look very familiar to you. I showed it to you just a couple slides ago. So my experimental method is almost virtually identical to the previous study. The primary difference is the addition of a catheter in this study. So like before, the transducer creates a single treatment path down the center of the clot. Treatment's poised, spaced half millimeter apart like before. Now, one kind of thing that's kind of interesting is the actual penetration of the clot itself. I just want to show you the process for doing that. So on the left in the middle, you can see my method for piercing the clot before I introduce it into the flow system. On the right-hand side here, you can see a beam mode image indicating the catheter here and then the clot itself. So we see a pretty good cross-section of this occurring. I also want to talk about my doses for this, because for this study, right, we keep our acoustic parameters the same, but we're changing our dosage scheme. So we're going to go from the bottom to the top here. So for the bottom, this is the largest dose, and this is similar to that seen in catheter-directed thrombolysis. At the 4.54 micrograms per milliliter. At the next lowest dose, at the 2.25, this is similar to what we call a pharmacomechanical dose. So this is a dose that's commonly used in what are called pharmacomechanical studies. This type of study uses lytic along with mechanical energy to destroy tissue. That, again, should sound very familiar. That's exactly the sort of study that I performed. So I want to choose this sort of dose to compare to literature so we can see how we're doing compared to other kind of studies. And then to really test the power of histotripsy, I wanted to go with about 1/10 of that dose too. And of course, I want to include my controls at 0. Oh, and then if you're curious too, the acoustic parameters I used were 20 cycle pulses at the highest pressure, so 35 megapascal peak negative pressure. So like the previous study, I measured D-dimer and mass loss, but this time around I wanted to kind of expand on our cast of characters a bit. So we know that when TPA acts on a clot, it lyses the fibrin structure and produces fibrin degradation products. Before, we only talked about D-dimer, but we know that a whole slew of fibrin degradation products are created, ranging in size from 260 kilodaltons all the way up to 2,300 kilodaltons. So I wanted to measure all of the fibrin degradation products in order to really see how histotripsy breaks the fibrin mesh. Is it possible that we just didn't see histotripsy creating the D-dimer fragments, but maybe it's possible that historypsy, cleaved off those larger chunks and created larger fibrin degradation products. So I really wanted to investigate that too. So for our results here, we're going to start off with our mass loss, and I'll show you D-dimer later. So pictured here are the average mass loss values for clots exposed to a range of lytic conditions. Blue bars correspond to no histotripsy, orange bars correspond to histotripsy. Stars indicate significant increases within a lytic group. What I really want to point your attention to right here is this blue bar here. So this is sort of our clinical equivalent here, which is our highest lytic dose for no histotripsy. So we want to compare our histotripsy treatments to this bar. What's kind of interesting is that it turns out that for doses as low as 0.23 micrograms per milliliter, so for this orange bar and this orange bar and this orange bar, these are non-inferior to this highest dose, this blue bar here. We actually do see a similar sort of effect with D-dimer, where just like for mass loss, combining histotripsy and at least the 0.23 micrograms per milliliter of lytic results in non-inferior D-dimer production as the current clinical standard scheme. And now I also want to just call your attention to, again, the fibrin degradation product analysis. So pictured here are histograms for the fibrin degradation product concentration for a couple of different experimental arms. So I want to first talk about this top row here. So for this top row, this is for no lytic that's administered either without histotripsy, so that's our top left, or for histotripsy, and that's our top right. What's interesting about this that I want you to take away is that there is no difference essentially in concentration between these two, right? So this would indicate pretty conclusively that histotripsy itself probably does not generate any fibrin degradation products, right? It's not working on its own to cleave the fibrin mesh itself. Now, on the other hand, what happens if we do add in lytic, right? And we compare with histotripsy and without histotripsy. So we can look at that for this bottom row here. So for this bottom row, this is for our highest lytic dose. On the left is for no histotripsy. On the right is for histotripsy. You can see as the skewness kind of changes between these two histograms that we're more likely to produce more fibrin degradation products when we introduce histotripsy with this highest lytic dose. So what did this second study show? If nothing else, I want you to take away that histotripsy can reduce the amount of thrombolytic necessary for clot destruction, at least when we're measuring by mass loss and D-dimer. So by estimating, right, if we say we're using 1/20th the lytic dose and we're assuming a 2-hour treatment time, this treatment could actually significantly reduce the probability of any procedural bleeding complications. And additionally, it could actually lower the overall financial cost of DVT by about even 80%. We also gained some cool insight into how histotripsy enhances clot destruction. So as shown with the fibrin degradation product analysis, we see that histotripsy itself doesn't produce any of those fibrin degradation products when lytic is not present, which again suggests that the breakdown of fibrin is due to the enhancement of the fibrinolysis, right? We're getting better fluid mixing, which helps the TPA cleave the fibrin mesh more efficiently. And it's not due to just the mechanical destruction due to histotripsy itself. So with that, I think that concludes a good portion of my research, and I hope that at the end of this talk, you all have a good appreciation for not just the imaging side of ultrasound, but its therapeutic applications as well.
Thank you very much, Dr. Hendley. That's very interesting and very neatly constructed experiments. Next, we have Dr.